Good morning, friends. We'll start with chapter 12, API 580. Risk management with inspection activities. Managing risk by reducing unnecessary through inspection. The risk can be managed by inspection. Inspection itself doesn't arrest the mitigation damage mechanism or reduce risk, but the information gained through effective inspection can better qualify the actual risk. Impeding failure of pressure equipment is not avoided by inspection activities unless the inspection precipitates risk mitigation activities that change the POF. Inspections serves to identify, monitor, and measure the damage mechanisms. Some damage mechanisms are very difficult or impossible to monitor with just inspection activities. Metallurgical deterioration that may result in brittle fracture may form forms of stress corrosion, cracking, and even fatigue. Establishing and implementing a comprehensive program for IOWs. The terms with an unacceptable risk to the owner user shall be assessed for potential risk management through inspection plans or other risk management strategies. Depending on factors such as the remaining life of the equipment and type of damage mechanism, risk management through inspection may have little or no effect. Examples of such cases are follows. Corrosion rates well established with equipment nearing end of life. Instantaneous failure resulted to operating conditions such as brittle fracture. Inspection technology that is not sufficient to detect or quantify deteriorate adequately. Too short a time frame for the onset of deterioration to final failure for PDK inspection to be effective. High cycle fatigue cracking. Event-driven failures. Circumstances that cannot be predicted. The most practical and cost-effective risk mitigation strategy can then be developed for each item. Usually, inspection provides a major part of overall risk management strategy, but not always. Establishing and inspecting strategy based on risk management, risk criteria, ranking risk drivers, equipment history, number of results of inspection, types and effectiveness of inspection, equipment in similar service, and remaining life, mode of failure of the damage mechanism, time interval between the onset of deterioration and failure, speed deterioration, determination, capacity, capability of examination technique, scope and extent of inspection, frequency of inspection. Managing risk with inspection activities. The effectiveness of fast inspections is part of the determination of the present risk. Frequency of inspection. Increasing the frequency inspection may severe or better define, identify, or monitor the damage mechanisms, and therefore better quantify the risk. Both routine and turnaround inspection frequencies can be optimized. Coverage. Different zones, areas, inspection of an item or series of items can be modeled and evaluated to determine the coverage that will produce an acceptable level of risk. For example, a higher risk of piping system may be candidate for more extensive inspection using one or more ND techniques targeted to locating the identified damage mechanisms. An assessment may reveal the need of focus on parts of vessel where the highest risk may be located and focus on quantifying the risk rather than focusing on the rest of vessel where there are perhaps only low risk deterioration process occurring. Tools and techniques. The selection and use of appropriate inspection tools and techniques can be optimized to cost effective and safely quantify the POF. As an example, profile radiography would typically be more effective than digital characteristic electronics for thickness monitoring. In cases of localized corrosion, procedures and practices. The inspection procedures and actual inspection practices can be impact on ability of inspection activities to identify, measure, and or monitor damage mechanisms. If the inspection activities are executed effectively by well-trained and qualified inspection, the expected risk management benefits should be obtained. Internal on-stream or external inspection risk quantification by external on-stream and external inspection should be assessed. It is worth noting that invasive inspections in some cases may cause deterioration and increase the risk of the item. Moisture ingress to equipment leading to stress corrosion cracking. EASCC, internal inspection of glass-lined vessels, removal of passivating films, human errors in startup pre-streaming, increased risk associated with shutting down and starting equipment. Managing inspection cost with RBI. Inspection costs can be more effectively managed through the use of RBI. This same strategy allows consideration of reduction of inspection activities in those areas that have a lower risk of or where the inspection activities has little or no effect on the associated risk. Achieving lowest life cycle cost with RBI. RBI should enhance the prediction of failures caused by damage mechanisms. This turn should give user confidence to continue the operating equipment safely closer to the predicted failure date. By doing this, the equipment cycle time should increase and the life cycle cost decrease. Upgrade construction material or replace specific items can then be developed. Other risk mitigation activities. Described in the previous section, inspection is the often effective method of risk management. However, inspection may not always provide sufficient risk in mitigation or may not be most cost-effective method. Equipment replacement and repair. When equipment deterioration has reached at a point that the risk or failure cannot be managed to an acceptable level, replacement, repair, or is often the only way of mitigation the risk. Removal of deadlocks. Equipment modification, redesign, rerating, fitness for service, change of metallurgy, addition of protective lining coating, removal of deadlocks, increased corrosion allowance, physical changes that will help to control, minimize deterioration, insulation improvement, injection prior designing changes, resizing of the relief device. Emergency isolation. Emergency isolation capability can reduce toxic explosion or fire consequences in the event of release. Proper location of the isolation valves is the key to successful risk management. Risk mitigation. Remote operation is usually required to provide significant risk reduction. To mitigate flammable and explosion risk, operators need to be able to detect the release and actuate the isolation valves quickly within a few minutes. Longer response times may still mitigate effects of ongoing fires or toxic release. Emergency depressurizing, de-inventorying, modify process, establish integrate operating windows. Integrity operating windows. IOWs should be established to process parameters, both physical and chemical, that could impact equipment integrity if not properly controlled. Example of process parameters include temperature, pressure, fluid velocities, pH, flow rate, chemical or water injection rates, level of corrosive constituents, chemical composition. It is a key process parameters for IOW should be identified and implemented. Upper and lower limits established as needed. The deviations from these limits should be brought to attention of inspection engineering personnel. Particular attention to monitoring IOW should also be provided during startup, shutdown, and significant process upsets. Reference API 584. Reduce inventory. This method reduces magnitude of consequences. Some examples include the following. Reduce, eliminate storage of hazardous feedstocks of intermediate products. Modify process control to permit reduction of inventory contained in surge dumps, reflux drums, and other in-process inventories. Modify process operations to require less inventory holdup. Substitute gas phase technology for liquid phase. Water spray delouse, water curtain, blast resistance construction. For this, okay, we'll stop here.